In this video, we'll be talking about partial fraction decomposition, which is going to be the last technique of integration that we're going to learn. Um, we're going to be using our calculator a lot, so make sure you have a calculator. It's not really necessary, but it really simplifies a lot of stuff later on, and you're going to see that in a little bit. But for now, here's what we have on the board. So we have seen techniques that have allowed us to integrate specific rational functions. Now remember, rational functions are basically a ratio, numerator, denominator, where you have polynomial expressions in both numerator and denominator. So for example, we've learned that the integral of du over u is nothing more than just the natural log of u plus c, and something a little bit more complicated like the integral of du over u to the second plus a to the second is equal to 1 over a inverse tangent u over a for the argument plus c. The big question becomes, what about something like the integral of 3x over x to the second minus x minus 2? So when you look at this problem that we have here on the board, there is no technique that allows us to just integrate this. I mean, initially it looks very simple compared to everything else or compared to what we've seen so far. However, there's no, technique that we know of that will do this. However, maybe we could rewrite this 3x over x to the second minus x squared in a way that will allow us to easily integrate this. So I'm going to tell you this. The integral of 3x over x squared minus x minus 2 dx is actually the integral of 1 over x plus 1 plus 2 over x minus 2 dx. All right? Now, the question now becomes, how do we go from this into two separate rational expressions? Well, the answer to that is partial fraction decomposition. Okay? So I'm going to teach you how to do this. And like I said, it's really going to help if we have like a TI-84. All right? Something that can do matrices. Now, don't worry. This is not going to be a very intense lesson in how to perform linear algebra, especially for those who have never seen it before. I'm going to show you what you need to know. Sorry for the repeating there. But I'm going to write down a little paragraph here. I'm going to pause the video, and then when we come back, you're going to see everything there, and we're going to explain it. All right, so here's the key to applying partial fraction decomposition. And normally, we just abbreviate it as PFD. So this can only be applied to a rational expression where we have P of x in the numerator, Q of x in our denominator, and we can only apply this if the degree of the polynomial is less than the degree of your denominator. If that is the case, you can go ahead and use partial fraction decomposition, which I will show you how to do that. On the other side, if your degree of P of x is greater than the degree of Q of x, you're going to have to go ahead and use long division, just like back in algebra class, to rewrite the quotient in the form a of x, where that's the quotient, plus r of x over q of x. And then you can go ahead and use partial fraction decomposition on r of x over q of x, provided it needs it, okay? So I think a good idea first is let's go ahead and let's do an example where partial fraction decomposition is not needed. Because this is the big thing you got to worry about. Just because you have a rational expression doesn't mean you're going to be doing partial fraction decomposition all the time. You need to slow down and evaluate what you have first and then make your move from that. So here's the problem we're going to be looking at here. Let's evaluate. x to the second plus 3x plus 5 all over x plus 1 dx. Okay, so here notice the degree of the numerator, degree of p of x is 2. The degree of q of x is 1. And since 2 is greater than 1, we're going to go ahead and we're going to use long division. Now, if you have something nice like what we have here and you want to use synthetic division, that is fine by me. That's what I'm going to do. So I'm going to write out my synthetic division algorithm here. I'm going to copy down the 1 and just go ahead and use synthetic division to figure out what the quotient would be. Negative 1 times 1 is negative 1. 3 plus negative 1 is 2. Negative 1 times 2 is negative 2. And 5 plus negative 2 is 3. Therefore, our quotient is going to be x plus 2 plus 3 over x plus 1 for our remainder. Therefore, I can go ahead and say, well, the integral of x to the second plus 3x plus 5 all over x plus 1 dx is actually the integral of x plus 2 plus 3 over x plus 1 dx. And you can see here we have a much easier integral now to perform. So going from left to right, the integral of x is going to be 1/2 x to the second. The integral of 2 is 2x plus, now I guess I'll do this off to the right. Let me just draw like a little red line here. The integral of 3 over x plus 1 is really just 3 times integral of 1 over x plus 1, which we're going to use u substitution. All right, so u equals x plus 1, du equals dx. So we get the integral, we get 3 times the integral of 1 over u du, which we know that to be 3 times the ln of u plus c. All right, and then when we go back and we substitute what u is, we get 3 times the ln of u of x plus 1 plus c, and that is exactly what I'm going to put over here into my final solution here. And there you go. So this would be a situation where the numerator is larger than the denominator's degree, and you just go ahead and use long division. I went ahead and just used synthetic division because what was really nice is this was a linear factor, and whenever you have a linear factor in your denominator, that is screaming synthetic division. All right. Now the question becomes, what if we don't have this scenario? So let us look at this example here. So we're going to evaluate the integral of 3x plus 2 all over x to the third minus x squared minus 2x dx. So if we just look at what we have here, remember, look at the degrees first. The degree of the numerator, so the degree of px is 1. Our degree of q of x is 3. So in this scenario, 1 is less than 3. So we're going to be thinking partial fraction decomposition. You could go ahead and try to use u substitution on this. It's not going to work. All right? So now the question becomes, all right, how do we do this? Well, the way that we set this up, okay, is we want to try to factor that denominator first, all right? And the reason for that goes all the way back to algebra class. So we're going to go ahead and we're going to go back in time real quick. And we're going to look at a problem where we had something like this. All right, something very simple. 1 over x plus 1 plus 1 over x plus 2. When we were to go ahead and add these two things together, all right, our goal is to find that lowest common denominator, right? And for our problem right here, the LCD would be the quantity of x plus 1 times the quantity x plus 2. That would be the first thing you would do. Then the second thing you would do is build your equivalent fractions. So I'm just going to put build equivalent fractions. All right. So it would be 1 over x plus 1 times something is going to give us our mysterious fraction where, or our mysterious ratio where we have the denominator of x plus 1 times x plus 2. So what's that? What's this thing that we're going to multiply by? Hopefully all of you are sitting there going, well, it's just x plus 2 over x plus 2. In fact, once you got really good at this, you didn't have to even do this step. You would have just came over to here on the left-hand side and just wrote it as such, which is fine. All I'm doing is breaking it up, all right? All I'm doing is just breaking it up here. But you would end up getting 1 times the quantity x plus 2. And then the other equivalent fraction would be 1 over x plus 2. You'd have to multiply this by something so that you get that magical denominator. And yes, if you're sitting there thinking, well, that would be x plus 1 over x plus 1, I would completely agree with you, and that would give us 1 times the quantity x plus 1. But the key to this is the fact of the matter that when we build our equivalent fractions, we would write just one big numerator here, and then you would write one big denominator as well. And notice, no matter what happens in that numerator, you have a factored version of the denominator. So that's exactly what we're going to apply here, all right? We're going to do the same exact thing. We're going to try to factor that denominator. Now, it is extremely important that you do this. And the reason is because whatever remains, you're going to have to make a decision. I'm going to show you how to make that decision. So, in the numerator, we still have 3x plus 2. But that denominator will factor into x times the quantity x minus 2 times the quantity x plus 1. So you'd have to factor out your GCF, which would be an x, and then you would be left over with a trinomial that factors into x minus 2 times x plus 1. But here's where the big thing kicks in, and I'm going to go ahead and I hope I have enough room right here. And there it is right there. This is going to help us to determine what we do. All right? So this is taken directly from Paul's online notes. I just copy and pasted it. And basically it just says, if you are integrating a rational expression involving polynomials, that is what we are doing. Where the degree of p of x is smaller than the degree of q of x. That is also what we have. You will factor the denominator as completely as possible and find the partial fraction decomposition of the rational expression. So how do you do that? Well, if you look at our denominator, we have 3 factors. We have an x, that's the first factor. We have the quantity, x minus 2, that's our second factor. And then finally we have the quantity, x plus 1. That is our third factor, okay? More importantly, each one of those factors are linear. And remember, and I hope you remember this by now, a linear factor is a factor where the variable's degree is a 1. So if you look at each one of these factors, each one of them, their highest degree for that specific factor is a 1. Therefore, we have linear factors and they are non-repeating. So we call this just non-repeating linear factors. So that is, getting out a different color highlighter for us, that is right here. So this very first option, if you want to put a little note, and I definitely would, this first option here is what we call a repeating linear factor. All right, zoom out a little bit more. There we go. I think that looks okay. It's good enough for government work for now. So if you look on the right-hand side, it says, let's go back. The non-repeating linear factor, q of x, which is ax plus b. If you have that, the term in the partial fraction decomposition is going to be a capital A over ax plus b. All right? And that is huge. Okay? So this is how I break up this problem. I have the integral of 3x plus 2 all over x times x minus 2 times x plus 1 dx. And this is going to break up into the integral of a over x plus b over x minus 2 plus c over x plus 1 dx. In other words, the three fractions that I must have added together to get the result, 3x plus 2 over x times the quantity x minus 2 times the quantity x plus 1, is a over x plus b over x minus 2 plus c over x plus 1. Remember, it goes back to like just that basic algebra that we learned a while ago. So now the big question becomes, okay, how do I find A, B, and C? And to be honest with you, it's very simple. It's just a lot of algebra. So this is how we find those. What we know is this. We know that these two integrals are the same exact integral on the board. In other words, and I'm going to write a big red equal sign, these two things are equal to each other. That implies 3x plus 2 over x times x minus 2 times x plus 1 has to equal a over x plus b over x minus 2 plus c over x plus 1. Which also means that if I were to try to simplify the right-hand side, I would have to find a common denominator. And then I can combine them all. So that's exactly what I'm going to do. So just watch how I do this real fast. We already know what our common denominator is. It's right here. It's staring you in the face. It's right here. That's the common denominator. And like I said, if you had a really good algebra teacher or a really good like basic arithmetics teacher, all right, they would have shown you how to build equivalent fractions and not do the little shortcut thing. And if you're wondering what am I talking about? Did you forget? What I'm saying is the shortcut would be this right here. This is the shortcut that we were all taught. And although I agree with it and it's like, okay, it's a shortcut, I do not like this at all because it completely negates what you're trying to do, because too many times students just memorize this without fully understanding what they're doing with it. All right? The building equivalent fractions thing would be this. And I'm going to do it once on the right-hand side just to show you what's happening. The building equivalent fraction would be a over x. I know I have to multiply this by something so that I get x times x minus 2 times x plus 1 as my denominator. What is that magical number 1? Because remember, you can't change a fraction's identity. You can only multiply by 1 and still maintain its identity. Therefore, we're going to multiply a over x by the quantity x minus 2 times x plus 1 over the quantity x minus 2 times x plus 1, and you end up getting a times the quantity x minus 2 times the quantity x plus 1. This is what you end up getting, and this is what we mean by we're going to build equivalent fractions. So what I'm going to do here is this. I already know these denominators on the left-hand side that's highlighted in blue, and now on the right-hand side that is also highlighted in blue, are already the same. The question becomes, what are the numerators? So, I'm going to write, and I hope you follow along with this, and if you need to, go back and look at the video, okay? What I'm going to write is this. On the left-hand side, I'm going to write 3x plus 2. And on the right-hand side, I'm going to write a times the quantity, x minus 2 times x plus 1, plus, and now I need to think about, okay, I know what my denominator is. What else would I need to multiply b over x minus 2 to generate that denominator? Well, since you already have the x minus 2, which is right here in your denominator, I'm going to multiply b by x times x plus 1. And then I'm going to multiply c by x times x minus 2. And I'm going to go ahead and just do all of my algebra here. So it's going to take a little bit of time, but I want to show you where everything is coming from, okay? Because that is by far the most important thing, okay? So on the left-hand side, we still get the 3x plus 2. On the right-hand side, we get a times x squared plus x minus 2x minus 2. And before I move on, I'm going to simplify this. Positive 1x minus 2x is minus x minus 2. So there's the first simplification. Plus, the next one's easy. It's going to be bx squared plus bx. And finally for c, it's going to be cx squared minus 2cx. Okay? Now, I'm just going to distribute the letter a. So we get 3x plus 2 equals ax to the second minus ax minus 2a plus bx to the second plus bx plus cx to the second minus 2cx. Now, we're going to group all like terms. All right, we're going to group all of our like terms. So the left-hand side doesn't change. It's still 3x plus 2. But on the right-hand side, I get ax to the second plus bx to the second plus cx to the second. We're going to put parentheses around that. Plus, let's group all of our linear terms together. Okay, so parentheses, it's going to be negative ax plus bx minus 2cx. Okay? And then finally, if there are any strictly linear terms, strictly constants, you put them off all the way to the right. So, plus negative 2a. All right. And this is the last step here before we actually have to use our calculator. You will notice in each grouping, they all have an x squared. For the first group, for the second group, they all have x to the first. And then the third group is just our linear. This is our constant term. It's just our constant term. I keep saying linear by accident, but it's just our constant term. So we get 3x plus 2 equals a plus b plus c with x to the second right factored, plus negative a plus b minus 2c with a right factor of x, and lastly, negative 2a. Now, sometimes this is kind of difficult for students to see, but it's actually very simple once you see it. And here's what I am talking about. On the left-hand side, we have 3x plus 2. Notice there is no x squared term on the left-hand side, okay? So what I'm going to do here is this. I'm actually going to copy and paste this. It'll let me here. So let's go ahead and let's copy and paste this because I really want to drive a point home here. Hopefully I can get this all on just one screen. Yeah, I think that'll work. So we have 0 x to the second on the left-hand side. In other words, the left and the right-hand sides have to be equal to each other, just like all the way up here where we said these two integrals have to be equal to each other. Which means all these terms, a plus b plus c, when I add them all together, it has to equal 0. So, a plus b plus c has to equal 0. Also, negative a, oops, didn't want that. Also, negative a plus b minus 2c has to equal positive 3. It just has to. So, negative a plus b minus 2c equals 3. And finally, we'll use this color, I guess. Negative 2a has to equal positive 2. So, negative 2a has to equal positive 2. And now, if you notice here, we have a system of equations in which we could easily go ahead and solve this, okay? So there are multiple ways to solve this. Any of them will give you the same answer, all right? Personally, I like doing more brain work than writing, so I like to use matrices for this. And what I mean by that is I understand how matrices work, and therefore I can use my calculator and easily do this. Or you can go ahead and you can use backward substitution. Like, for example, right here in this third equation, we know negative 2a equals 2. I'll just divide both sides by negative 2. We already know that a equals negative 1. Which means I can go back up into either of these equations up above and substitute in negative 1. And then I have a system of equations where you have two variables. So you can go ahead and you can do solving this the long way. But I'm going to show you how to use your calculator to do this. All right? Now remember, we already know a equals negative 1. So we're going to keep that there. Here's how we're going to do this inside of a calculator. First thing we're going to do is we're just going to go create our matrix. Now, to create a matrix, if you've never done this before, it's a system of equations where in the first row, it's going to be equation 1. The second row will be equation 2. And the third row will be equation 3. Then, in each column, it's going to represent each coefficient of each unknown value. So in column 1, it's going to be all the coefficients for A. In column 2, it's going to be all the coefficients for B. And then in column 3, it's going to be all the coefficients for C. And when you have it equal to some output, sometimes you will see it drawn as a dotted line, and sometimes they don't even draw it. But this is called, hold on one second, let me write the word result. This is called an augmented matrix. And the reason why it's augmented is because we have outputs on the far right side. So the outputs are going to be 0 for equation 1, 3 for equation 2, and 2 for equation 3. So the only thing we have to do is just go ahead and assign A, B, and C for equation 1, 2, and 3 respectively. So it's going to be 1, 1, 1 for equation 1. Equation 2, remember, they're just the coefficients. Negative 1, 1, and negative 2. And then for equation 3, it's only negative 2 and then 0 and 0 because there is no b term, nor is there a c term. So we have our matrix right here. And here's how we go ahead and we type this into our calculator. So I'm going to get my calculator out here. Let me go ahead and detach the LCD so we can see this. All right. So if you've never done this before, please pay attention. What's great, it's a video. You can always pause it, go back, and see it again. To create a matrix, the first thing we're going to do is we're going to come down to this inverse X button, and right above it says matrix, okay? So I'm going to hit second matrix, and I'm going to go to this word over here called edit. So I just scroll over twice and hit enter. Now, the matrix A, and then it says 3x4. What that means is a 3 by 4 matrix. Rows always come first. Columns always come second. All right? So we have 3 rows. If we go back into our problem here, notice we have a 3 by 4 matrix because we have 3 rows, equation 1, 2, and 3. And then we have 4 columns, A, B, C, and then our result. So this is a 3 by 4 matrix. So let's go back to our calculator here. We're going to hit 3 by 4, so 3, enter, 4, enter, okay? And we're going to go ahead and just type in the coefficients. So remember, row 1 was 1, enter, 1, enter, 1, enter, and then 0. Now, as soon as you fill out row 1, it will automatically go down into row 2. So we're going to do row 2 now. So negative 1, enter, 1, enter, negative 2, enter, and that's going to be a 3. And finally, negative 2, enter, 0, 0, 2. And make sure you hit enter after you hit 2. Just make sure you hit enter. That way you know this is the matrix, okay? You can always double check to make sure you typed it in correctly by using the navigation keys, the up, down, left, and right if you want. Or the other way you can guarantee to make sure you're correct is if you go back to the home screen, which is what I'm going to show you. I'm going to show you how to check just to make sure. Go back to the home screen. Go back to the matrix. Here's matrix A. All you have to do is make sure it's highlighted. Hit enter and enter. And you're going to see it right here. Now notice, this will not give you the little dotted line. You have to know that this is an augmented matrix because we know the outputs. But as you can see here, it's 1, 1, 1, 0. In fact, let me see if I can just move this over here. There we go. So you can see 1, 1, 1, 0, negative 1, 1, negative 2, 3, and then negative 2, 0, 0, 2. So far we are looking great. Now, this is all fine and dandy, but the calculator only has the matrix stored. Here is the function that you're going to want to use inside of your matrix or inside of your calculator. RREF, and then you're going to do matrix A. Now, the RREF, if you're interested, stands for row reduced echelon form. So if you've never taken a linear algebra course, sometimes in certain pre-calc courses or like college algebra courses, they will go over matrices and they'll go over Gaussian elimination, row reduced echelon form, like what does that look like? They'll go over QR decomposition. They even go over backward substitution. This is not the class for that. We don't have the time. So we're going to just go ahead and use RREF, all right? So let's go back to our calculator here. And I'm going to show you how to do this. All right, there we go. So go back to the matrix. Sounds like we're watching the movies. But we're going to move over to math. We want the calculator to do some math for us. So go over to math, and we scroll all the way down until we see RREF. So notice you have REF and then RREF. You want the double R, all right? Row reduced echelon form. So we tell the calculator, okay, do this function. So we hit enter. And then we have to tell the calculator what matrix we want row reduced echelon form. So we go back to the matrix one last time, and we're going to tell it, go ahead and do matrix A. So notice here I have RREF, parenthesis, matrix A in brackets, and the parenthesis, just like what I have written directly underneath in the middle of your page. And as soon as I hit enter, I think I just said that twice. Oh well, maybe I will edit that out. But anyways, here's what you get. This on the left-hand side, the 1, 1, 0 in the first row, -1. And then you have 0, 1, 0, 1.33333, all this stuff, and then 0, 0, 1, -0.333 repeating, all right? The left-hand side, the 1, 0, 0, 0, 1, 0, 0, 0, 1, that is called echelon form. So what I'm going to do is I'm going to go ahead, and I just want to copy this into our notes. All I want is this, because I want to be able to write. All right. So this right here is called row reduced echelon form. Okay? Each one of these outputs is going to be A, B, and C respectively. Now, I'm with you. I hate the repeating decimal. So for those who didn't know, you can always do this in your calculator as well. So let's go back to our calculator here. We're going to do this again, row reduced echelon form of matrix A, except math, answer fraction. And when you do the answer fraction, it's going to go ahead and tell you exactly what they are. So for us, A equals -1, B equals 4/3, and C equals -1/3. So I'm going to write it real nice and neat on the right-hand side. A equals -1, B equals 4/3, and C equals -1/3. All right? And also, I want to get rid of all this because I just want one nice picture of our screen that shows everything that we need. All right. Yeah, this is going to look great. So, oops, let's do this a little nicer. There we go. This is A, B, and C, which means all the way back up here, A was -1, B was 4/3, and C is -1/3. And even to clean this up a little bit nicer, I'm going to put the negative out front. 4/3 is just 4/3. And then -1/3 is right there. So, what are the three fractions that you added together to get 3x plus 2 over x times x minus 2 times the quantity x plus 1? Those three fractions were -1 over x plus 4/3 times the quantity x minus 2 minus 1/3 times the quantity x plus 1. And congratulations, this is your first partial fraction decomposition. You are taking the result of adding fractions together and you're decomposing it into its component parts. That's what this whole thing is all about. All right? So, in fact, you know what? I'm going to copy and paste this. You'll see why in a second. So, what do we do with this? Well, we were asked to integrate 3x plus 2 over x times x minus 2 times x plus 1 dx. And now we will finally do that, because what we are going to do is we're going to integrate negative 1 over x plus 4 over 3 times the quantity x minus 2 minus 1 over 3 times the quantity x plus 1 dx. And what ends up happening is we end up getting a really nice integral where we can separate these into like 3 little problems. I'll put a plus there for now. Keep it nice and simple. Now we could just do these 3 little mini problems, or 3 little mini integrals. And it makes everything just so much easier. So to finish this, we're going to move any negatives and any constants out front. So negative integral of 1 over x dx plus 4 over 3 times the integral of 1 over x minus 2 dx minus the integral, we got a 1/3 out front, 1 over x plus 1 dx. And going from left to right, we get negative ln of x plus 4 over 3 natural log of x minus 2 minus 1/3 natural log of x plus 1 plus c. And this is how we do partial fraction decomposition integrals. You take a rational expression where the numerator degree is less than a denominator degree. So degree of p of x is less than degree of q of x. And if this is the situation, partial fraction decomposition where it is a bunch of algebra all over again. So, with the remaining examples in class, I'm going to not greatly speed up, but what I really need to do is I need to hit each one of the potential partial fraction decompositions that we can run into. And what I mean by that is this. I just want to copy and paste this. All right, here we go. And I want to maximize this as much as I can. There we go. I think that looks pretty good. And the reason why I want to go over this is because if you notice, right here we had non-repeating linear factors. But notice that's not the only one that we can run into. All right, we can run into non-repeating quadratic functions or quadratic factors. And sometimes we refer to this as just irreducible, okay? Put a box around this and put irreducible, meaning you cannot reduce it, obviously. I teach a lot of algebra courses, so it's like I always find myself repeating words that I think you already know, so please don't, roast me in the comments for that. All right, so on the left-hand side, we have non-repeating linear factors and non-repeating irreducible quadratic factors. On the right-hand side, notice you have this exponent of a k for both of these. All right, so what that means is we have repeated factors. So these are repeating factors. So I'm just going to write repeating over here. All right. And you will see how, you will notice how they change, and they definitely change. Okay. So I'm going to try to do an example of each one of these for us. All right. You got to be careful and make sure you read the homework as well. Because in some of the questions, it just says set up, do not integrate. All right. So, you know what I mean? Before you just start diving into a problem, make sure you read the directions, because the last thing you want to do is do a setup problem and then you didn't read the directions and you actually integrate and it took you like an hour to do this, when in reality it was only a 5-minute problem. So make sure you read the directions before you just jump right in, okay? Now let's go ahead and do some examples. So here's a nice problem. Let's evaluate the integral of x minus 2 all over the quantity 2x minus 1 squared times x minus 1 dx. So if you notice in this problem, first, just by looking at it, it's already factored. Our denominator already factored. We love that. Second, right here, this is a repeated factor, okay? It's a repeated factor, and it's also linear because that x is raised to the first power, and in the second factor, the x is also raised to the first power as well. And finally, because we have a repeated factor and it's raised to the second power, we also know that the degree of p of x is going to be less than the degree of q of x. 1 is definitely less than 2, so partial fraction decomposition. All right, so let's go ahead and let's see how we set this up, okay? So here comes the partial fraction decomposition. We have x minus 2 over 2x minus 1 quantity squared times x minus 1. Now, to break this up, because we have repeated factors, we need to do it twice. In other words, we're going to have a over 2x minus 1 plus b over the quantity 2x minus 1 squared. Finally, the quantity x minus 1 is just going to be put underneath c. But let's go back and let's see why I wrote it like this, okay? So we have 2x minus 1 quantity squared. Since k is equal to 2, we have to write it 2 times. So that would be it right there. If we had k equal to 3, then I would have a over 2x minus 1. In fact, let me write that down. So I'll write it over here on the right-hand side. If it'll let me, there you go. So if we had like 2x minus 1 to the third, well, then I would have wrote it as a over 2x minus 1 plus b over 2x minus 1 squared plus c over 2x minus 1 cubed. Yes, you have to do that, okay? The x minus 1 was just one factor, wasn't repeating, so I just wrote it over c. Or under c, I mean, not over c, under c. All right, so go back to our problem. Now, it's just a matter of algebra all over again. So I'm going to help us out with this. Remember, you already know what the denominator is going to look like. In fact, sometimes I've seen students in the past, they will just rewrite the denominator so they can physically see that repeated root. All right. So on the left-hand side, we get x minus 2. On the right-hand side, notice we have 2x minus 1 already in the denominator. So we need another one. And we need the x minus 1. For the letter b, we already have both 2x minus 1s in the denominator. Therefore, all it needs is an x minus 1. And finally, the c already has the x minus 1. So I'm just going to go ahead and write 2x minus 1 and then another 2x minus 1. Okay? Now from here, it's just a lot of algebra. I'm going to help us out with this one. So we get a times the quantity, 2x to the second, minus 2x minus x plus 1. And remember, negative 2x minus x is going to be minus 3x. So it's minus 3x plus 1. For the letter b, it's just bx minus b. And finally, for c, if you recognize that you have a binomial squares pattern, you could save yourself a lot of distributing just by using the formula. In case you don't remember the formula, that's fine as well. I'm just going to write c times the quantity, 4x to the second, minus 2x plus 1. So we get a 4 or a negative 4 in the middle. So negative 4x plus 1. All right. Now distribute, and now this is where I'm going to do everything in once. So hopefully you can follow. I'm going to distribute the a, and I'm going to group all my like terms at the same time. So for example, we get 2a x to the second plus 4c x to the second in a group. Then we're going to get negative 3ax plus bx minus 4cx. And finally, we're going to get positive a minus b plus c for our constant terms. All right. So hopefully you can see that. Maybe you can, maybe you can't. All right. And now I'm going to go ahead and just factor my x squared x out. So, I get 2a plus 4c x squared plus negative 3a plus b minus 4cx. And then we get a minus b plus c on the far right side. All right. From here, remember, when you look at the right-hand side of the equation, you have 2a plus 4c, and that has to equal an x squared term. Unfortunately, we do not have an x squared term on the left-hand side, but that's fine, because here's what we know. 2a plus 4c, and yes, I put a space here on purpose, will equal 0. For the variable x to the first, a linear term, we have negative 3a plus b minus 4c, and that has to equal 1, which is the coefficient on the left-hand side of the equation for the linear term x. And finally, we have a minus b plus c equals negative 2. Therefore, our augmented matrix will look like 2, 0, 4, 0. For the first row, negative 3, 1, negative 4, 1 for the second row, and 1, negative 1, 1, negative 2 for our third row. And I'm just going to go ahead, back into my calculator, type all this in, and then we're going to row reduce echelon form to get each one of these letters, A, B, and C respectively. So let's get the calculator out. I'm going to try to move this up here so I can still see everything. All right. This time, I'm going to speed up a little bit. Matrix. Edit. It's a 3x4. And then the coefficients in row 1, 2, 0, 4, 0. Row 2, negative 3, 1, negative 4, 1. And finally, row 3 is 1, negative 1, positive 1, and negative 2. Then I quit, go back to the matrix, tell the calculator, let's do some math. So we scroll down to RREF, and we're going to row reduce echelon form, matrix A. I'm going to hit math, answer fraction, just in case I get decimals. So hit enter. And here we go. So we end up getting the following. All right, I had a typo in my calculator, so I had to fix it real quick. But here's what you end up getting. We're going to get, oops, I needed that. Can I pin this to the top? No, it won't let me. But I bet you I can pin this to the top. Nope, it won't let me. That's fine. So we get 2, 3, negative 1. That's fine. 2, 3, negative 1. So let me just fill this in real quick. All right, and what this means, everybody, is A equals 2, B equals 3, and C equals negative 1. Okay? So we can go ahead, substitute these in, and then we can try to integrate this as easily as possible, or as easily as we can. So remember, we had the integral of x minus 2 over the quantity 2x minus 1 squared, x minus 1 dx, is equal to the partial fraction decomposition of a is 2, so it's going to be 2 over 2x minus 1 dx. Actually, we'll write it all as 1 first. Plus b is 3 over the quantity 2x minus 1 to the second, minus 1, because that c is equal to negative 1. So it's going to be minus 1 over x minus 1 dx. And then, going from left to right, we're just going to separate these. Integral, we're going to pull the 2 out front of 1 over 2x minus 1 dx. Plus, we're going to pull the 3 out front. Integral of 3 times the integral of 1 over 2x minus 1 to the second dx minus 1 over x minus 1 dx. And going from left to right, we get the natural log of 2 over 2 times 2x minus 1. All right, you have to use u substitution here. So you get, and the 2 is from the 2 out front, and then 1/2 when you use u substitution. So that's going to reduce. Plus, once again, you would have to use u substitution here. So this is going to be, it's actually going to be a minus 3 over 2 times 2x minus 1 minus the ln of x minus 1 plus c for a final result. So since this video is already an hour long, I'm going to cut it off on this video. But in the next video, I'm going to do a couple examples where we have repeated terms, okay? Repeated quadratic terms. That's what I want to focus on, the quadratic ones. So I'll see you in the next video.